So we have the graph, Baz. I got it printed out. 36 inches by 24. It's quite incredible. I love it. For this talk, the dimensionless quantity connecting sun-like stars to red dwarfs on a mass radii diagram. The Cassandra Ratio. I know there are a lot of people who are still new to this theory. The Cassandra Ratio, I'll link it to the bottom. All this paper says is if you have an object that's at a mass between 1 and 1/2 the mass of the sun, you can take that and you can derive how wide it is, what its radii is. And that ratio is 9.6 over 1,000, or 9.6 over 1,000, or about 1 in 100. So if you have a star that is 800 Jupiter masses, then that star is going to be 8 Jupiters wide. It's very simple. And you can go in reverse. If you find a star that's 8 Jupiters wide, you're going to find out that it's about 800 Jupiter masses, and vice versa. So we can make corrections here. And I had linked this. Now, obviously, it goes the opposite direction as this graph does. So imagine this top area right here is on the right side of this diagram. So it's just flip-flopped. But so you have the y-axis, which is mass. Again, the mass is correct. And then you have a Jupiter radii, which is on the x-axis. So here's the really big objects, really wide objects, I should say. Here's the really massive objects. And as the mass is lost, the radius decreases. So you have shrinkage and you have mass loss. And it stays pretty stable. And if you lose the mass quicker, or if you've lost a lot of mass quicker than the radii shrinks, I think I got that backwards. Basically, you can determine if the star is going to be flaring or shrinking based on where it sits on this diagram. So if you have an actual star and you measure it to be down here, then it's going to be flaring. If you have it up here on this side, so these stars up here, the star is going to be shrinking. So what it does is it flares, shrinks, flares, shrinks, flares, shrinks, flares, shrinks, all the way down until it reaches about here. And then different processes take over. Of course, it gets far more complex than that. And there's many other things involved in that. That's a very big abstraction. But the reason why I did this, and the reason why I called it the Cassandra Ratio, is that it's very obvious to me that a star like the sun is not going to become a red giant. There's no way. A star like the sun would be about right here, and then it cools and collapses into a red dwarf. So the Cassandra Ratio has objects between here and here, this area right here. But then once it gets to around late stage red dwarfs and brown dwarfs, the Cassandra Ratio goes right out the window, because then you can lose mass at different intervals. You can have the star's gravitational field is very weak, so if it gets in orbit around another hotter host, it can lose mass a lot faster or slower, depending on if it's a rogue object and it doesn't actually orbit in close to a hotter host, which means it can keep its atmosphere, so it can have a lot more time to build that interplanetary core, which means then it starts branching off. So you have high transformation curves up here and low transformation curves down here. So a star that would keep a lot of its mass and not be ripped apart by a hotter host would be able to make it really, really big. So it would be up here. And if you have a star that gets ripped apart really fast, really, really fast, then it can go way down here and just become a core remains of some dead object. But for the most part, you have stars evolving in that manner. But the establishment, the astronomers, they say sun-like stars are supposed to get really old, or sun-like stars are actually way the hell over here, right here. And then, obviously there's no spot for them there because they have sun-like stars being billions of years old, which is, well, I hate to word it like this, but it's idiotic to say that a sun-like star is billions of years old when clearly there's a pattern there. The young stars that shine are only millions of years old. The billion-year-old objects are highly evolved. They're way the hell down here. But I don't know why they sort of keep that mentality. Now, I got distracted. The Cassandra Ratio, the reason why I named Cassandra is it's a term that originates in Greek mythology. Cassandra was a daughter of Priam, the king of Troy. Struck by her beauty, Apollo provided her with the gift of prophecy. But when Cassandra refused Apollo's romantic advances, he placed a curse, ensuring that nobody would believe her warnings. Cassandra was left with the knowledge of future events, but could neither alter these events nor convince others of the validity of her predictions. Here's a painting by Evelyn de Morgan of Cassandra. Notice how she's a bit frustrated. She's pulling her hair out, being able to predict the future, but nobody believes her. So it's the Cassandra Ratio. The Cassandra Ratio is the ability to predict the future of the sun, but when I tell astronomers this, they don't believe me. Even though it's pretty damn well obvious that the sun isn't going to become a red giant, it's going to cool and collapse to become a red dwarf. And then it's going to continue on a basic line of evolution, becoming a brown dwarf, and eventually many hundreds of millions of years later into something resembling Jupiter and gray dwarfs and Neptunes. And all these objects are going to start popping up in the Kepler and test data, and then the Gaia data and the Plato data, and then astronomers are going to be more and more and more lost and confused because none of their theories are panning out. None of it makes any sense. And the only way it can make sense is if they just trash all the previous ideas that were invented in the 19th and 20th centuries. Well, you can keep some of the ideas, but trash most of them and go back to a very simple understanding that stars are not these exotic things. They're young planets. That's all they are. But anyways, there's this Cassandra syndrome, the Cassandra ratio, I should say. And that being said, this has to do with the star K2-33. Here's an artist's impression of K2-33. And here's the young star, and here's the old star transiting. Astronomers call old stars planets. If anybody's still new to this theory, they sort of have their semantic reasoning all screwed up. That's what caused this mess to begin with. Why they can't understand basic astronomy and astrophysics. But it says here the mass of the main star is 0.56, and the radius is 1.05. Now, the one of those two has to be wrong. Now, being that the star is only about 3,400 degrees Kelvin, it's, a little more than half the temperature of the sun is currently now on its surface. It's definitely a red dwarf. And red dwarfs have lost a lot of their mass, which means, it's probably, about half the mass. So the temperature lines up, 0.56, the mass of the sun, the mass lines up, yet the radius is sort of, they have it bonkers. If you were to put that radius on the Cassandra diagram, the star would be way the hell over here. What are you doing over there? If you have a temperature of 3,400 degrees Kelvin about, and you have a mass of 0.56, you belong way over here. So somewhere down here. This is where K2-33 belongs. And also, that being said, they say, well, the reason why we have it as its huge radius is because it's so bright. Well, the reason why it's probably bright is because there's stuff being reflected. There's stuff reflecting off the star, making it brighter. You know, Jupiter and Venus. Venus isn't shining. Jupiter isn't shining. They're reflecting a lot of the light from the sun. So, I mean, I was reading some papers, and they have a debris disk around this star. Okay, and they're saying, well, the star is really bright and its radius is huge, like the sun. But that's very strange, because what about all the material that's in orbit around this object? Wouldn't you suppose that it would be reflecting off that material, making it appear a lot brighter than it really is? Just like the reflecting, or the albedo of Jupiter and Venus, where Venus is really bright in the night sky, but it's not shining of its own light. It's reflecting the light from the sun. So it just means that this red dwarf is reflecting a lot of light from a debris disk, and it's making it appear to be a lot wider than it really is. But actually, it's giving a false impression among these astronomers that this object is as wide as the sun, but it's not. Anyways, I just wanted to point that out and show you that this actually exists. This smooth continuum. And these are all the Kepler stars. Of course, I have a list of all the Kepler candidate stars in the paper here. All right, guys, let's check out that. Oh, and hi, Celeste.